I don't quite have a theme song yet, but I'm working on that. If you have any ideas, submit one. But I will tell you that percent composition problems are 100% JBran approved. Yay. What we're going to take a look at is how do you look at a compound like sodium oxalate in this first example and compare the percentage of sodium to carbon to oxygen, and how can you use that to identify certain chemicals in the laboratory setting. With these examples, I'm not going to do every element in the compound. I'll just do a couple because they're all done the same way. So for example, for the first one, to determine the percent composition, we're going to have to compare the percentage of sodium to the mass of the entire compound. Okay, I'm back. Whew. Probably didn't seem like a long time for you, but I actually paused the video and helped a student solve a problem. Oh, crazy, I know. Alright, I'm back. And we were just talking about how I'm only going to do sodium and I'm only going to do carbon. And if you were to do oxygen, it would be calculated the exact same way. So let's start off with the sodium. The first thing you want to do is you want to write down what the molar mass of your element is. And if you look at the periodic table, you would see that sodium is 22.99 grams for every mole. That's the molar mass that we find on the periodic table. Now, that's for 1 mole. This is where you have to analyze the problem and see how many moles do you have. We actually have 2 moles of sodium for this. So we would write 2 moles of sodium in, on the bottom, you would put 2 moles of sodium in our solution of 1 mole of Na2C2O4. This number here, this number 1, correlates to the coefficient in front of the entire compound. And I'm going to delete that so it doesn't confuse you there. So that's where we get this number 1. So if we were doing oxygen, we would put 4 moles of oxygen if we were to do that one. So now that compares how much we have. This is going to give us our part. So the part of sodium, and we need to compare that to the whole. And the whole mass would be 1 mole of Na2C2O4 has a certain molar mass. Now I calculated this ahead of time. You can pause it and try to calculate it yourself if you want to. But this is where off to the side you do Na times 2 gives you a mass, C times 2 gives you a certain mass, and O times 4 gives you a certain mass. When you add all of that up, you end up getting 134.00 grams per mole. And you may be off by a tenths or a hundreds, and that's just due to rounding. That's okay if you're slightly off. Different periodic tables will have different things. So we plug in that number here, and we have 134.00 grams of Na2C2O4. I'm going to delete this so it's not in our way. And on the paper that you guys are working on, you guys can write stuff like that out in the margins, and you can keep kind of the clean part here in the middle so I can follow along with your work. And then what we have to do is multiply the entire thing by 100, because that's going to give us the percent. So even though we did a lot of crazy things, when you take a step back and look at it, you basically have a part, which is Na. You have 2 of them, and it's divided by the whole mass. And when you put everything in your calculator, you'll end up getting 34.31% of sodium in the solution. Now the next one I'm going to go through and write out fairly quickly. And again, we're only going to do sodium and carbon because oxygen would be done the same way. But if we take a look at carbon, carbon has a molar mass of 12.01 grams for every 1 mole of carbon. We need to figure out how many carbon atoms we have. we actually have, let's go back when we have 2 moles of carbon, and that comes from the coefficient right here, or the subscript right there. So 2 moles of carbon for every 1 mole of our compound, Na2C2O4, and then we multiply that by our conversion, 1 mole of Na2C2O4 moles per gram. So 1 mole is 134.00 grams of Na2C2O4 times 100 to give us a percent, and we end up getting 17.93% of carbon. When you do the third one, you'll see that it is 47.76, and when you add all 3 of those together, you're going to get very, very close to 100. You might not get exactly 100 because of rounding in different periodic tables and so on and so forth. So that's the basics of percent composition. You're dividing the part of it by the whole mass to determine what percent you have. Some things you need are the individual molar mass and the total molar mass of the compound. That's all I have for set 1. There'll be another video on set 2, and I need an exit theme song too. I'll work on that. But in the meantime, just always remember that percent composition problems are 100% JBrand approved. Have a great day.